Hi, I'm happy to be at the 5th International Conference on Applied Zoology 2022. And I am thankful to Dr. Rasul Ashar for invitation to this lovely meeting. And my name is Yusuf TUTAR, and I'm working at University of Health Sciences at Faculty of Pharmacy, Division of Biochemistry, and we have also a graduate program on molecular oncology for medical doctors. And my topic today is dissolving combinatorial effects to make innovative breast cancer drugs. So far, for 2 decades, I'm working on breast cancer and its immune subtypes to reveal molecular mechanism to design small molecules as drug candidates. Well, we solved the mechanism of these subtypes, but designing a molecule is not enough to inhibit the cancer cells at all if you target just single micromolecule. And there are subsections that we have to deal for effective inhibition. The first one is the non-coding RNAs, and these non-coding RNAs basically forms a connection between cytosol and mitochondria, and effective non-coding RNAs that we found is pseudogenes and microRNAs. Pseudogenes basically affect heat shock proteins, and isoforms of heat shock proteins at cancer cells increases. So this suppresses small molecule induced cancer cell inhibition. So we also designed molecules that will bypass these steps. And another key point is the energy metabolism. As you know, most of the subtypes depend on Warburg effect. That means relatively low or no oxidative phosphorylation is observed. Well, actually, in triple negative breast cancer subtypes, oxidative phosphorylation is observed. So what we design is inducing some key TCA cycle intermediates and blocking glycolysis. And all these will drive the cells to the cell death through apoptosis and through senescence. But the last mishap is the cancer stem cells, and we monitored the cancer stem proliferation through 4 genes to understand the effect of designed inhibitors over cancer stem cells. So we use the PCR arrays to understand the signaling, and the nice thing of our design is to use not only the subtypes but also to use the resistant form of these subtypes. And the nice thing to reveal the molecular mechanism is to compare resistant form with the normal cancer cell line, because that will provide extra information. But what we found is the compound that affect the resistant form will not affect the cancer cell line. So by using the templates that are effective, on cancer cell lines and resistant cancer cell lines. We did some in silico studies as well, and we designed salicylate and indazole derivatives from aryl hydrazanol compounds. And what we did first is to understand the mechanism is we did gene enrichment studies. And these gene enrichment studies provide us a good screening because we can see if the compound is worked on programmed cell death, cell cycle, signal transduction, metabolism, and such. So that is our first evidence if our compounds are a good potential drug candidate. And in the second step, when we did the PCR array studies, we saw that there are several biochemical processes that work fine for our compounds, like the cell cycle perturbation through CDK4 and CDK6. And we also inhibited EMT, as well as we enhanced oxidative phosphorylation. And of course, there are two types of senescence. One drives the cells to the cell death, and the other one is oncogene-induced senescence. And this is actually useful for cancer cells, and this is also inhibited with our compounds. And the nice thing of our compound is the energy metabolism, and this is regulated through CHRP that actually shows a combination effect of not only the glycolysis or the TCA cycle, but also the pentose phosphate pathway. So the compounds are pretty good at activation of these energy pathways. So the last thing that I want to go through is, of course, the stem cells, cancer stem cells, because we know that some subpopulation of cancer cells are basically formed from stem cells. And these stem cells, even though you inhibit the cancer cells, these stem cells proliferate the cancer cells, and well, that will decrease the efficiency of the drug or the compound that we designed. So that's why we basically insist of working on these cancer stem cells, and our compounds are effective in inhibiting the cancer stem cell, breast cancer stem cells. Well, we also tested if the pseudogenes and HSP90AB4 pseudogene is one of them. The compounds are effective not only decreasing the stem cell population, but also the pseudogene. So we trace the stem cell population through 4 genes, NanoXStat3, SOX2, and POF5F1, and the expression levels of these 4 genes for different compounds are decreased. So other thing that is important of our compound is the compounds induced immune system, and another nice pathway in here is node signaling pathway. As you know, this induces immunity, and our compounds induce this signaling pathway. So our compounds not only induce immune system, but also suppresses pseudogene microRNA effects as well as the cancer stem cells. So we have a combination effect of those compounds, and actually we are working on animal experiments right now, and the compounds shows superior properties through ADME and anti-cancer properties. So we are on the process of patenting, and the nice thing of our compounds is also they display their activity at lower micromolar concentration. So the compounds have the potential to be a clinical drug. So I would like to thank you for your kind attention, and I again appreciate the invitation. And I would also would like to emphasize the founder of our project, and this is TÜBİTAK with the grant number 219Z142. Thank you very much.